Hello everyone. In this video I want to talk about some applications of the Jacobian matrix for a robot. So here, to make life simple, we are dealing with a planar 2DOF robot, and both joints are rotary, and the angles right now are 30 and 45 degrees for theta 1 and 2, and the size of the links are 1.5 and 1. So here we're gonna basically answer a bunch of different questions. One is, if I want this robot to keep this load of 20 Newton upright, stationary, how much torque would you need to apply on each one of these joints? So if this is tau 1 and this torque is tau 2, the question is how much they should be if we have to hold this load in static condition. And if you remember from my previous lectures, in static analysis of a robot, we can show that the torque vector, which is basically tau 1 and tau 2 in this case, this is equal to Jacobian transpose times what? Times the force, or in general you call it wrench vector at the end effector. In this case, since we only have 2 degrees of freedom, this wrench is basically Fx and Fy at the end effector. But if you have rotational degrees of freedom, it can also be the torques that the end effector is applying to the environment. Okay, and the first thing is, what is Jacobian for this robot? Again, if you look at my previous lectures, you know that the Jacobian for this robot is, in general, negative A1 S1, negative A2 S12, and then negative A2 S12, then A1 C1 plus A2 C12, and then A2 C12. Okay, so this is the Jacobian 2 by 2. Again, if we only focus on the x and y motion of the end effector, nothing else, no rotation, no z motion, which they're all 0, by the way, you know. Z motion is 0, theta x, theta y are 0 for end effector. You only have a theta z, which is simply theta 1 plus theta 2, and it's not really an independent degree of freedom. So here we only look at the x and y motion of the end effector. This is your 2 by 2 Jacobian, okay? So now, at this specific angle, theta 130 and theta 245, well, then 1 is going to be 30, as I said, and 1, 2, which is 1 plus 2, is going to be 75 degrees. We calculate the sines and cosine. We replace A1 and A2. And in this case, if we plug in the numbers, here I have this MATLAB code that can give you the numbers. So here I'm using MATLAB symbolic, and I tell you why. So here I define time and theta 1 of t and theta 2 of t, A1 and A2. And I define the Jacobian just like I showed you. And the reason I do it is because later I need to take a time derivative of the Jacobian as well using the diff command. So that's what I do. And then I substitute in J for theta 1 of t, theta 2 of t, A1 and A2 these numbers. I use 30 degrees, 45 degrees. Of course, I convert them to radians because here I have sine and cosine functions, not sine d and cosine d. And then 1.5 and 1, I replace A1 and A2, so I do a substitution. And then it's going to be symbolic, so I use the eval command, and then I use a VPA to convert it into numerical number. So if I just go ahead and run this section only, right, you're going to get the Jacobian matrix. So that's your Jacobian matrix, negative 1.72, negative 0.966, 1.56, and 0.259, okay? So I'm using 3 numbers here, and that's what you see in this VPA of 3, right? And that's what my Jacobian is showing. Okay, so this is the Jacobian of the robot in this specific configuration for these 2 specific angles. And now, if I plug that here, right, if I plug that Jacobian right up there, and also for the end effector force, I'm also going to need what? I'm also going to need the force. So what are the forces on the end effector, or actually what are the forces that the end effector applies to the environment? Pay attention, this F is the force that the end effector applies to the environment, not the environment applying to the force, okay? So this is basically, in general, as I said, we call it the wrench, right? Because there could be other degrees of freedom. So this is the wrench applied by end effector to the environment, right? Or to the object it is basically dealing with, it is handling. So in this case, the wrench that is applied, the force in the y direction has to be the same as that 20, and there should be no x force because we don't need it in stationary. So basically this guy is 0 and this guy is what? 20, positive 20, again to keep it upward. If I multiply that by that Jacobian, I'm going to get the torques that are needed, and this is what you can see I'm doing down here. So I define my twist, my wrench, and then multiply it by transpose of this J, and here we go. Here are tau, right? And you can see the tau is shown, of course, with a ton of decimals, so if we want, we can limit it to like 4 and 5. But you see that 31.157 Newton meters and 5.176 Newton meters are the numbers that we need on each joint. Okay, so here you see I added the VPA to only show with 4 meaningful numbers instead of a ton. And basically these are the two torques that I need on the joints, right? And again, this F, we call it what? We call it the wrench. Okay, that's one of the applications if I want to know how much torque to hold a weight in static condition. That's the answer to question 1. Let's go to question number 2. It says, if I want the end effector to have a velocity of 2.5 and 1.6 meters per second along x and y, how fast should I rotate each joint? So this time the goal is not to keep this load. The goal is, in stationary, the goal is to have this end effector move like this velocity, where this x component is 2.5, right? So this is v of the end effector in base. And this vertical component is like 1.6 meters per second, right? We want to know if we want to spin these two joints as q1 dot and q2 dot, or theta 1 dot and theta 2 dot, right? How fast they should be. If you want, even you can call them omega 1 and omega 2, but here let me just call them theta 1 dot and theta 2 dot, right? So how fast should you rotate each pin such that end effector achieves such velocity? And again, if we know, this is called the inverse velocity problem. So the end effector velocity is given. You want to find what? You want to find the joint velocities. So in general, the end effector velocities, we use this vector xi, and this involves all of the velocities of the end effector, including vx, vy, vz, and omega x, omega y, omega z. Now in this case, we only have vx and vy component, right? And again, this guy, we call it what? We call it the twist vector. And in this case, it's 2.5 and 1.6. And if you know, this guy is equal to what? This is equal to J inverse, this is equal to J times Q dot, vector Q dot, where this Q dot is, in this case, theta 1 dot and theta 2 dot, or Q1 dot and Q2 dot. And here the left side is given, the right side is unknown. Therefore, Q dot is what? It is J inverse times xi. Okay, and that's all we need to do. And J inverse exists if the robot is not in a singular position. Clearly here you can see that the robot is not in a singular position, because you can check it with J, right? The determinant of this matrix is clearly not 0. And if I use inverse, right, as you can see here, and multiply by xi, I should be able to get the required velocities. You see 2.067 counterclockwise and 6.26 clockwise, right? Negative means clockwise, positive means what? Counterclockwise. So now you can see how fast each joint should spin. So that's second problem. What's the third problem? Here is the direct velocity problem. It says, let's for a moment lock joint 1 and just spin joint 2 with a theta 2 dot of 5 radians per second counterclockwise, also with an angular acceleration of 3 radians per second square counterclockwise. So here I'm giving you both theta 1 dot, theta 1 double dot, theta 2 dot, and theta 2 double dot. And I want you to tell me how fast the end effector moving and what is the acceleration of the end effector. Okay, so this is the direct velocity problem. This time your q dot in this case is 0 for theta 1, and then what? As you can see, positive 5 for theta 2 dot, right? And then q double dot is what? 0 and 3. Okay, the angular acceleration of the joints. And the question is, what is v of the end effector? What is a of the end effector? Well, v of the end effector in this case is the same as xi, right? So xi, which is the v of the end effector in the base, this is simply equal to j times q dot. So we multiply that j by q dot, and that's it. Now, acceleration of the end effector, here we have to take a time derivative from this. And if you do that, then acceleration of the end effector in base, here you have to take derivative of this. And the thing is, j is not constant. It's a function of the joint angle, so it has time derivative as well as q dot. So it's a product, so it's going to be time derivative of j with respect to time times q dot plus j times what? Q double dot. Okay? And q dot and q double dot are given. J is calculated. The only thing is j dot. What is j dot at this moment? And that's what I did earlier. If you remember, I used the diff command here to take time derivative of j, and I define my j such that I can take derivative from it because I use time and I define theta 1 and 2 functions of time. So clearly you can see that here, if you look, my j is a function of time, and if I take derivative, my j dot is also going to be a function of time. Here you see, in it you have diff of theta 1 and t, so that's theta 1 dots, right? This is what? This is theta 2 dots. So this is j dot in general, which you can also go ahead and perform a derivative on this guy, right? If you perform a derivative on this one, basically, so d of j with respect to time, you can take a derivative here if you want. Well, let's go ahead and do that just for the sake of practice on calculus. So a is constant, s1 is going to be c1, but there is a theta 1 dot as well, so it's going to be negative a1 c1 theta 1 dot, then negative a2 c1 2, and then times the derivative of the argument, which is theta 1 dot plus theta 2 dot. Okay, and then the second term is this guy, basically, just negative a2 c1 2 times sum of the two dots. And then here you have a1 c1, so it's going to be negative a1 s1 theta 1 dot negative a2 s1 2 times sum of those terms, and then again negative a2 s1 2 times sum of those terms. So that is j dot, which you can also see here. Okay, that's exactly this one. And then again down here, you see, now I define my q dot at 0 and 5, q double dot at 0 and 3. Then I multiply the j. This j val is the same as j, just numerical numbers, right? J is a symbolic matrix. When I plugged in the numbers in them and got a number, I call it j val. So I'm multiplying what? That j, right, by the q dot, and that is going to be xi, or v of the end effector, as we just mentioned down here, right? And then for my xi dot or A, you see I multiplied j dot by q dot and j by q double dot, right? So here, if I run this section for you, you can see that the velocity of the end effector is going to be negative 4.83 in the x, 1.294 in the y, and acceleration of that is going to be negative 2.898 meters per second squared along x and 0.7765 along y. Okay, so you see I can do direct velocity and direct acceleration problems also using j and the derivative of j for acceleration. Okay, so I got this one taken care of. Finally, manipulability, which is a measure of how close the robot pose is to a singularity. And one of them that I mentioned in my videos is called Yoshikawa's manipulability measure, right? And that's basically the product of the singular values of the matrix JJ transpose under a square root, which for a square matrix like this, for a square Jacobian matrix, the Yoshikawa's measure, right, mu, let's see, where do we go? Down here. The Yoshikawa's measure mu is simply what? The absolute value of determinant of j. If j is squared, in general, as I said, it's the square root of what? Product of the singular values of what? The matrix JJ transpose, right? And so here I just need to find determinant of j and absolute value of that. We know if this number is 0 or very close to 0, means I'm at the singularity, or very close to singularity. The bigger it is, the further away I am from a singularity. So here, this is what I do. I get the absolute value of j-val, determinant of that, and show it. And clearly this number is not 0. You see it's 1.06. So I'm away from the singularity, and of course I am. You can see that the robot is not at complete extended position or retracted. So theta 2 should not be 0 or pi, and that's 45 here. So this is clearly off. Now, the other thing is show the manipulability ellipse as well as the force ellipse. Okay, draw them. How would you draw that? Well, if you looked at my previous videos, you know that the manipulability ellipse is basically an ellipse like this, and it has a minor axis and a major axis, and these axes are the eigenvectors, the axes are the eigenvectors, the direction of them, right? The direction of these axes, if I show them for you here, like this and this, these directions are the eigenvectors of JJ transpose, and the magnitude of them are what? Are the square root of eigenvalues of JJ transpose. Okay, so that's what we need to do here, right? I need to fast clean up something here. This is not square root, the mu, and this is just j. Okay, so the mu is just the product of the singular values of j, or it is equal to square root of determinant of JJ transpose. Okay, this is mu in general. For a square, this is for a matrix, a j that is not a square. For a square matrix, it just becomes this. Okay, so just a correction. This is the Yoshikawa's manipulability original format, and so these are singular values. These are singular values of j. Okay, so that's Yoshikawa, and I got rid of j since I mentioned it here. So now we have to go and find the eigenvalues and eigenvectors of JJ transpose, take a square root of the eigenvalues, and then we draw the manipulability ellipse and then the force ellipse, which is basically an ellipse of similar size, just perpendicular to that. So, and I can do it on the robot, but first I need to get the numbers. So here that was the mu, and then here you see I'm multiplying JJ transpose, taking eigenvalues of that and assign them to V and D. V's are eigenvectors, these are eigenvalues. And then I'm showing the eigenvectors, and then I'm showing the square root of the eigenvalues. Okay, so here if we go and run, you can see that this was the Yoshikawa's measure, and these are the two eigenvectors, right? The first column and second column, and these are those square roots. So in this direction, 0.78 and negative 0.6. The value should be about 2.5. In the other direction, which is 0.6 and 0.8, the value should be about 0.4 or something. Okay, so I have, and by the way, since these are only two of them, clearly in the 2D they are perpendicular to each other, right? And in general, if there is more, they should be perpendicular too. So these two are two perpendicular directions. One is 0.6 and 0.8, the other one is 0.8 and negative 0.6, okay? So if I go back here, and let's see if I can draw it on the robot. So here, the goal is to draw an ellipse centered at the end effector at this moment. So let's go ahead and draw an ellipse. If this guy allows me to rotate it, I don't think it does here. So I have to draw it with my pen. And so in the direction of what? In the direction of 0.8 and negative 0.6. So 0.8x, negative 0.6. So this is going to be something like this, right? In this direction, along this line, and the other one is 0.6 and 0.8, which is like this direction. In this direction, the semi-minor is 0.4. In this direction is what? 2.4. So it is going to be something big like this, right? And then shorter one in this direction, something like that. So this is going to be my ellipse. What's the meaning of this ellipse? This ellipse shows the direction that you can move the most and the least, or the fastest and the slowest. So in this direction, right, this is the slowest that you can go. This is the minimum that you can go. In this direction, the longer part is the direction that you can move fastest at the moment. So this is what? This is the manipulability ellipse, right, for this 2DOF at this point. And then the force ellipse is exactly like this, but it is what? It is perpendicular to that. So in this direction, you have a shorter one. In this direction, you have what? You have longer ones. So it's something like this, probably. Okay, so this is the force ellipse. And this one, as I said, is what? The manipulability. This one, the bottom one, shows in which direction you can move the fastest and the slowest. This one shows in which direction you can apply the maximum force and minimum force. So if I want to add them for you here, this is basically the Vmax direction. This here is what? The Vmin direction. But at the same time that this is Vmin, this is going to be Fmax. In this direction, you can apply maximum force. In this direction, you can apply what? A minimum force. Okay? So these are these two ellipses. In which directions you can move fastest, in which direction you can apply the max force and also the min. So you see in all of these, the Jacobian was involved, whether directly in inverse in forward velocity, directly plus its derivative in the acceleration, in singularity and how close you are to singularity, the determinant of that and the absolute value of it. In these ellipses, the eigenvalues and eigenvectors of JJ transpose. In the inverse problem, the inverse of it, and in the static analysis for how much torque, the transpose of it. Okay, so you see why this matrix is such an important matrix. And so many things in kinematics and kinetics of a robot do depend on J. Okay, so hopefully this example was useful to you, and I'll see you in the next video. Thank you.